Today, I received a damaged 1000-watt power inverter at my repair shop. The customer told me that several repair shops had already refused to fix it because of the complicated fault. In this video, I'm going to inspect the inverter, troubleshoot the power circuit, and see if this unit can be repaired and brought back to life. After opening the inverter, the condition turned out to be much worse than expected. Part of the PCB was completely burned out, and there were repair marks all over the board. That's probably the reason why so many repair shops refused to work on it. First, I'm going to remove the low-quality capacitors that were installed by the previous technician. After that, we need to completely remove all the burned sections of the PCB, because carbonized PCB material can become electrically conductive. If it isn't cleaned properly, the board could easily burn again after the repair. These are the capacitors installed by the previous technician. Although they have high capacitance, their ESR is also quite high, which causes significant heating under heavy load. I'm going to replace them with high-quality capacitors from JH. Their ESR is only around 1 to 2 milliamps, which is extremely low. Next, I'm going to use 3mm copper bars to rebuild the burned PCB traces. These are the V+ and V- power lines, which are connected directly to the main filter capacitors. After soldering the capacitors in place and securing them with adhesive, the whole assembly became extremely solid. Next, I'll give you a quick overview of the main sections of this inverter. Here we have a large aluminum heatsink with 8 MOSFETs mounted on it. These MOSFETs belong to the DC-DC conversion stage. The 8 MOSFETs are divided into 2 switching banks and are driven by a D882, B772 totem pole buffer together with a TC4427 MOSFET driver. The oscillator IC is a KA3525 running at 32 kHz. The small IC next to it is an op-amp used to sense the DC output voltage and provide feedback to the KA3525 for voltage regulation. Beside that is a 5-buck converter for the USB output rated at 5 volts 2 ounce. This is the main transformer. It has a primary winding of 2 + 2 turns and a secondary winding of 65 turns. The output voltage is rectified by 2 dual diodes and filtered by the large electrolytic capacitor beside them. The smaller transformer is used for the auxiliary power supply. It converts the battery voltage into the different supply rails required by the inverter, such as 12 volts, 5 volts, and 3.3 volts. These 3 tiny transformers are 15 volts isolated power transformers used to supply the A350 optocouplers in the H-bridge stage. These 4 optocouplers drive the 4 IGBTs, which convert the 400-volt DC bus voltage into 230-volt OS. After passing through the 3 mHz output inductor and the 4 μF capacitor filter, the inverter produces a pure sine wave at the output. First, we're going to check all the MOSFETs and IGBTs in the circuit. I already explained the testing procedure in detail in a previous video, so you can watch that for reference. Fortunately, all of the MOSFETs and IGBTs are still in good condition. After taking a closer look at the PCB, I found that all of the A350 optocouplers and Zener diodes had already been replaced before. However, after testing them, I noticed their values were abnormal, so I'm going to replace them with new components. The power supply resistors for the 3 small transformers were also badly burned. I'll remove the damaged parts and grind away all the carbonized material using a mini rotary tool. I'm now going to replace all the burned components. Since the PCB and copper traces in this area were completely destroyed, I'll use through-hole components and solder them on the backside of the board instead. It may not look very pretty, but it will definitely work reliably. As you can see, the 15-volt supply for the AT350 driver optocouplers is now present. Next, we're going to apply the main power and test the inverter again. This is the output waveform and no load voltage. Everything looks good. The MOSFETs are running cool, the no load current is low, and the output sine wave is very clean. Now we can finally reassemble the inverter back into its case. So the root cause of this failure was a problem in the 15-volt supply for the H-bridge driver circuit, which caused one side of the H-bridge to operate abnormally. This placed excessive stress on the main power transformer and the primary filter capacitors. Because the capacitors had high ESR, they overheated and eventually burned along with part of the PCB. Thank you for watching this video. I hope my repair process can help you troubleshoot and repair inverters with similar failures.